We have Justin Pombrio talking about inferring type rules for syntactic sugar.
Hi. Okay, so I'm going to tell you how to infer type rules for syntactic sugar. First of all, what do I mean by syntactic sugar? I mean any time that a piece of syntax in a language is defined in terms of the rest of the language. So for example, in Python, addition is syntactic sugar for a call to double underscore add, so I'll say that it desugars to double underscore add. Likewise in Haskell, list comprehensions are syntactic sugar, and so forth in a variety of languages. So syntactic sugar is useful because it splits a language in two. It gives you a large surface language that has all of the sugars in it for programmers to use, and a much smaller core language for tools to work over. But there's some downsides. So in particular, it tends to interact poorly with type checking. Let me give you an example of this. This is some rather innocent-looking C++ code that made the mistake of using iterators, which are defined in terms of templates, and as a result, you get an enormous error message. As another fun example, I myself was trying to learn a new language called Lux, and I was literally trying to write "Hello World" when I got this error message that exposed all sorts of sugar in the program that should have remained hidden. So what are some possible solutions to this? The obvious thing to do is to extend the type checker to handle the whole language. But this is kind of giving up. If every time we run into an issue of this form, we make our tools work over the whole surface language, then there wasn't much point in having syntactic sugar in the first place. So what I'm going to present instead is what I'll call resugaring type rules. And the idea is to automatically infer type rules for the sugars given type rules for the core language and definitions of the sugars. So let's see how this works with a very small example. So this is an AND sugar. So alpha and beta desugars to if alpha then beta else false. And we would like to construct a type rule for AND. So first of all, what property would we like this type rule to obey? Well, you just saw a very closely related correctness property in the previous talk, but I'll have a slightly different one. So isurf here means in the surface language, and icore means in the core language, and the fancy D is desugaring. So this is saying that I would like, for my type rule for AND, I would like that alpha and beta has a type T in the surface language if and only if its desugaring has the same type in the core language. In other words, desugaring should preserve scope. Now this is a slightly different rule than Will gave. He said if there's a type in the surface language, then you get the same type in the core language. In my case here, I'm inventing the surface language type rules, and so that if statement wouldn't be very useful because I could cheat and just say, oh, nothing has a type in the surface language, so the if vacuously holds. Okay, so we'd like to achieve this if and only if property. There's actually a very easy way to do it. We can introduce two type rules, one for the reverse implication and one for the forward implication. And now we're done, right? This property is going to hold. So I'll show how to get better rules than this after, but these will technically preserve the property. So first of all, I want you to notice of these two rules, the top one isn't very useful. The top rule is telling us how to type, is giving us an additional way to type check if. But if is already in the core language, so we already have perfectly good type rules for it. So we don't need this top rule. The bottom one, however, is interesting. It says how to type check and in terms of if. So let's see an example of how we could use this rule. I'm going to prove that true and false has type Boolean using the rule from the previous slide. So first thing to do is, using that rule, convert the and into an if. And then since if is in the core language, we can use the core language's type rule for if, which says that the condition needs to be a Boolean, and the then and else branches both have to have the same type, in this case Boolean, and so the whole thing is a Boolean. Okay, so technically this rule works, but notice that it's kind of a leaky abstraction. This type rule is mentioning if, which means that it's showing you the implementation of and. And kind of the whole motivation for this is that we would like to not leak the implementations of syntactic sugar. So I'm going to use, so let me show you how we can achieve a better type rule for and. The trick is going to be, we're going to construct a similar derivation, except this time we're going to start with a completely generic term with alpha and beta, where alpha and beta are unknowns. So as before, we'll use that same rule to convert the and into an if. And now, using the if type rule, the condition must be a Boolean, so alpha is a Boolean. Also, we can see that false is a Boolean, which is the else branch, so the then branch beta has to also be a Boolean. Now, alpha and beta are unknowns, but for any particular alpha and beta, if this derivation were to be completed, it would need to be completed with further subderivations proving that alpha and beta have type Boolean. So these are assumptions that we need to make. These are assumptions that if we make them, this derivation will hold. And as a result, we can actually, this derivation is largely redundant. We can take the whole thing and collapse it down to a single type rule by taking these unproved premises, alpha and beta have type Boolean, and using them as the premises of the type rule, and just copying the conclusion of the rule. Now I want you to notice two things about this type rule. First of all, it's no longer leaking the implementation of and second of all, it's the canonical type rule that you would expect. Okay, so that was a very simple example. Let me now show a somewhat more interesting one. So this is a list comprehension. It's saying with at least one clause. So alpha is the thing to be computed. The first clause, x arrow beta, is saying take elements from list beta and call them x. And this is allowing there to be additional clauses in the list comprehension. So gamma is 0 or more additional clauses. For example, in gray here, this concrete list comprehension is saying take all pairs of elements x and y from a list and produce a list of their products. Okay, so what is the desugaring of this list comprehension? So essentially we want to map and then map a function over the list and concatenate the results. So supposing that we're desugaring into a type checked language rather than one with type inference, then we need a type annotation on the function argument. So I've called that t here, but notice that t is unbound. Where are we going to get this from, and what should it be? So t here ought to be the type of the elements of the list. So we support this by allowing a construct called calc type in the definition of a sugar. So this is saying calculate the type of list of beta and say that it has type list of t, and then t is available to be used in the rest of the desugaring. Okay, so this is the desugaring of this list comprehension. Let's derive a type for it. So the first thing to do, as before, you don't need to read this, but this is the same kind of generic type derivation over this list comprehension. And I'm going to zoom in on a couple of its parts. So first of all, we use concat map here, which is a global function, and so we have a way of dealing with that. It's not very interesting, so I won't say anything more about it. Also, there's this use of calc type, and as before, these unproved premises. So let me first of all zoom in on calc type. So since we can use calc type in the definition of a sugar, we need a type rule for it. Here's that type rule. So on the bottom, this is saying we're going to calculate the type of E1 and call it T, and E2 is the rest of the desugaring. In the premises, this is saying, first of all, E1 had better type check to some type T1. Second of all, T1 had better unify with the type T that you said it would have. And finally, as a result of this unification, any free variables in T are available for use in the rest of the desugaring. Okay. Now, additionally, there's these unproved premises. So there's 3 of them, but 2 are the same, which is why there's 2 up there. And we need some sort of type rule so that we can tell exactly when it's okay to stop and admit something as a premise. So I call this type rule T premise. I draw it with a dashed line just to suggest that this is admitting something to be true rather than a proof. And here's the T premise rule. So it says anytime we have a purely surface term that doesn't contain any constructs in the core language, well, our core language type system isn't going to help us anymore. And so we might as well admit this as a premise. And so we just assign it a fresh type variable. Okay, now as before, we can take these unproved premises and make them the premises of a type rule for this list comprehension. Okay, so this is saying, first of all, beta should have some type list of T. And second of all, in the upper left, that's saying, if you recursively type check the rest of the list comprehension, and you're allowed to use X as you do this, whatever type you get is the type of the whole list comprehension. And that's what we automatically derived in this mechanistic way. Okay, so we implemented this in PLT redx and tested it on a variety of languages, essentially from the first half of TAPL. Let me just briefly show a couple more examples. So this is a let rec defined in terms of fixed point and the derived type rule, or the resugared type rule. And this is the derivation for a lambda with early returns defined in terms of exceptions and the inferred type rule. Okay, now let me come full circle and return to the original motivation. So the work that we did was simply to produce type errors, was simply to infer type rules for syntactic sugar, which will allow you to obtain type errors at the right level of abstraction. What we haven't done is work on actual error messages. Right, and there's a couple ways you might go about this. One is you might try to automate getting these in a nice way. Alternatively, you can do what's usually done and have a programming language developer write the error messages, but now they're given these type rules that are guaranteed to be correct as a useful starting point and guaranteed to talk only about the surface language and not say anything about their implementation. All right, happy to take questions.
Hi, William from Northeastern. So, very cool work, thank you. It looked like all of the type rules, or all the syntactic sugar you present are simple sorts of macros in the Lisp
Yes.
world. What if your macros contain computation? And I have a follow-up question depending on your answer.
Then this will not work. So the assumptions behind this work are the macros have to be defined in terms of pattern-based rules, and the type rules for the core language have to be syntax-directed.
Okay.
Yeah.
Okay. So have you thought about if you could support computation, supposing you had a sort of typed, staged computation system at the meta level? So instead of just using, typically in a scheme or Lisp bracket, et cetera, you have untyped computation at the meta level. But supposing you had like a typed staged metaprogramming system in the style of meta OCaml or something, do you think this work will let you have computation in your resugarings using sort of typed staged metaprogram?
If there was computation at the
Yeah. So if your computation language is typed and has a notion of the types of syntax objects. Okay, maybe it's a bit out of scope and we can take it offline.
Yeah, I want to think more about that. Yeah, that's a good question. Right. So basically, instead of pattern-based rules, you would have transformations on terms, but ones that are guaranteed to be well typed in meta ML style. But yeah, I should think more about that.
Question.
So you just said that you want your core language type rules to be syntax directed, but it looked on slide 14 as if the rules that you generate are not syntax directed. The premise of the list comprehension was not a subterm of the original list comprehension. Did I get that right? And if so, does it mean that you cannot necessarily produce rules that are based on desugarings to syntax sugar? The first premise doesn't exist syntactically in the conclusion. So I wonder if that is still considered syntax directed by your definition.
By the meaning of syntax directed that I'm using, this rule is syntax directed. The thing is, what I mean is which type rule matches should be purely a function of the syntax of the program. Right, so the fact is the conclusion of this rule is what's determining whether or not it matches, and the x0 beta is like doing a pattern match, and that needs to not overlap with any other type rule. Yeah. I understand that there's some variety in what syntax directed exactly means.
So from the inferred typing rules, are you able to generate a type checker? In the implementation we have is based on PLT redx, which gives you a type checker from these rules for free. So essentially, yeah. So you're guaranteed to be able to.
Only for the level of type checker that redx gives you.
Can you say something about what the limitations are, or under what circumstances we'll be able to do that?
Yeah, so for instance, redx will, you can ask it for type derivations, and if it finds and it will show you every one it finds, and if it doesn't find any, then it's just like, well, I didn't find a type derivation.
And this is introducing syntactic sugar at the expression level. What if the person was trying to introduce a new kind of type?
Very good question. Yeah, so way back at the beginning, my correctness property said that, let me actually just go back there. where was this? Yeah, so this property here was actually the place at which I ruled out desugaring in the types themselves. Because you notice that T is the same in the surface and core language. I believe the property you would want instead is that basically having a desugar T down there in the core language. There's some interesting implications of that I might be able to say more about offline.
Any more questions? All right, let's thank Justin.